Hey, welcome back. This lesson is going to be all about parametrizing surfaces. So from that last video lesson where we introduced parametrized surfaces and the activity that you did in class, hopefully you're starting to get a sense for what a parametrized surface is and maybe a little bit about why they'd be useful. In this lesson, I'm going to introduce you to a few strategies that you can use to come up with parametrizations of surfaces. What I'm going to try to show you is that if you have a strong geometric understanding of what's going on with a specific surface, then you can use that to your advantage to find a parametrization. Let's get into it. The way that I'm going to try to introduce those strategies is through examples. And so here's the first one. We want to try to find a parameterization of the paraboloid z equals x squared plus y squared. Now, as you might already know by now, there are a lot of ways to do this for this specific surface. That's really why I like using a paraboloid as an example. It's sort of simple as surfaces go, but at the same time, it sort of contains all of the complexities, or at least most of them, that you'll encounter when you're parametrizing surfaces. So just like a couple lessons ago, when we were talking about finding strategies for parametrizing curves, I'll encourage you to have the following question in mind anytime you're trying to come up with a parametrization of a surface. What will the roles of each parameter be? Remember when we were parametrizing curves, sometimes we wanted to think of the parameter t as being like one of the coordinates x, y, or z, or sometimes we wanted to think about it as angle as we were moving around a circle. So now, since we're parametrizing surfaces, there's going to be two parameters for every parameterization, and so it's going to be useful for us to be able to identify what the roles of those two parameters will be. And actually, we'll see from this series of examples that a single surface can have lots of different parameterizations that you can kind of get by thinking about different sets of roles for the two parameters. But for our first parameterization, the thing I want to observe about this surface is that it's the graph of a function. And since our surface is the graph of a function, we know something pretty useful about it. We know that for all of the points on the surface, one of the coordinates, in this case z, is determined by the other two. And this was sort of like that example we had for parametrizing curves, where we were able to solve for two of the variables in terms of a third, and we let that third variable be the parameter. Well, now for parametrized surfaces, we want to find two parameters. And actually, this observation kind of gets us there, because we have two variables, x and y, and if we know what x is and we know what y is, then we know what z needs to be. So let's let x and y be our parameters. But I'm not actually going to call my parameters x and y. I could, but I find that when you do that, it leads to some confusion sometimes. So I think it's always a good idea to use separate variable names for your parameters. So throughout this video, I'm going to use u and v as my two parameters for a surface. So what we're saying here is, let's let one of our parameters, u, be the same as x, and the other one, v, will just follow y. And so the usefulness of observing that this is the graph of a function is that once we know what x is in terms of our parameters and what y is in terms of our parameters, which in this case are very simple, we know what z should be. So since z is x squared plus y squared, in terms of our parameters, it's just u squared plus v squared. So our parameterization, which I'm going to call r with a 1 as a subscript, it has two input parameters, u and v, and again, x is u, y is v, and z is u squared plus v squared. There we go. Just from how we set it up, we're guaranteed that all the points x, y, z that could be output by this function satisfy this equation. That's always something you're going to want to check when you come up with a parameterization. Okay, so the main takeaway from this example is that anytime you're working with a surface that is the graph of a function of two variables, you can parameterize it by letting the parameters essentially be the two input variables. In this case, they're x and y, and then the third coordinate z is determined by x and y just by virtue of how functions work. But before we go any further, I want to kind of explore a little bit, what does this parameterization look like? In particular, when we're talking about parameterizations of surfaces, we want to be thinking about what the grid curves look like, because different parameterizations will give you different sets of grid curves on a single surface, and for various reasons down the line, it'll be useful to know what those look like. So let's jump over to a GeoGebra applet that will let us explore this a little bit further. So here we are in GeoGebra. This isn't a default GeoGebra setup or anything like that. This is an app that I made to help you visualize parametrizations of surfaces and grid curves. So I'll put a link on screen right now. And I'll also put a link to the app in the description of this video so you can go find it if you want to play along with it. What you can do with it is plug in any parameterization. The reason I'm using U and V in this video is because you have to use U and V here. It's the way it works. For our parameterization, remember we have x equals u, y equals v, and then z is u squared plus v squared. And then there's a few more things that you have to set up. It's not going to show the entire infinite surface. So what you're going to do instead is specify what's called a parametrization domain. In other words, you pick out bounds on u and v, and it will only show the portion of the surface where u and v range over those numbers. So this is called the parametrization domain. This window on the bottom left shows the parametrization domain, which is this square in the UV plane. And then the last thing is grid curves. So I mentioned grid curves before are the curves you get when you fix either u or v and look at the curve you get parameterized on the surface. So you can take this pink point here and drag it around the UV plane. And as you do that, you'll notice that there are two lines in the parameter domain. One is vertical. This is the line u equals, in this case, 0.66. So it's always a u equals constant line. And then the horizontal line is a constant v equals 0.46. And you can move the sliders here too if you want to move those lines around. But the important thing is to notice that as you're moving this around here, the picture of your surface is changing. So here's our surface. So by either moving the point here or moving the sliders, you can sort of see what the different grid curves are. And actually, all of the grid curves of this surface are parabolas. And there's a lot of geometric connections to make here. Because it's a paraboloid, any vertical slice of it will be a parabola. And actually, that's essentially what these grid curves are. The grid curves, when we fix u or v, are just the curves we get by intersecting this surface with x equals constant or y equals constant planes. All right, moving on. Here is our second example. And actually, it's just to find another parameterization of this same paraboloid. But we're going to do it a kind of substantially different way. So just a second ago, we were finding a parameterization by looking at this surface as the graph of a function. Now we're going to do it a little bit differently by kind of going more into the geometry of this surface. And by that, I mean we're going to essentially play a game that I made up. And the game is called Find the Circles. So by find the circles, I really mean find circular cross sections or circular slices of this surface. So for this one, this paraboloid, the thing that we'll notice is that it has circular cross sections in horizontal planes. So in other words, if you fix z and look at the corresponding curve that you get a circle. Okay, let's write that down. So I'm calling the horizontal plane that we're looking at the slice in, I'm calling it z equals u. So for now, I'm thinking of u as a constant, even though later on it's going to be one of our parameters. But the idea is if you look at the slice in a z equals constant plane, you get a circle, and you can write down the equation of the circle just by plugging in u here and writing it like it's a circle. So in other words, x squared plus y squared equals u. So thinking of this as just a curve in a plane whose axes are labeled with x and y, we get a circle, and the radius of this circle is the square root of u. So we found the circles. We found that for different values of z, the cross sections of this surface in z equals constant planes are circles, and moreover, we know how the radius of the circle depends on which z coordinate we're looking at. So going back to our guiding question of what should the roles of the parameters be, we're going to let one of the parameters be z, which we've already kind of written here, and the other parameter, well, if one of our parameters is picking out different circles, then we need the second parameter to be the one that moves around each circle. So another way to think about it is to parameterize this surface, every location is determined by which circle it lies on, and then the angle around that circle that you need to move to get to that point. So another way to say that is like the other parameter is going to be like theta, which is moving around the circles. Now, when it comes to actually writing down the parameterization, we already know that z is going to be equal to u. For x and y, let's go back to this observation and note that if z is fixed and it's equal to u, then x and y essentially need to go around this circle of radius square root of u. So let's parameterize in x and y a circle of radius square root u, which we do by square root of u, the radius, times cosine of the angle, which we're going to call v. And then for y, we have the same thing, but with sine. So this is saying that x and y both kind of traverse this circle of radius square root of u as v increases. And then the last coordinate, z, we've already said that's u. That's the thing that's picking up all of the different circles. So our parameterization, R2, will look like this. R2 of uv is square root of u cosine v, square root of u sine v, and then just u. Back in our GeoGebra app, I've put in the parameterization that we just came up with. I had to pick a different parameterization domain from before because now the parameters are serving different roles. So u is like the z coordinate. So I just decided, let's say u goes from 0 to 4. So that we have a paraboloid that goes from z equals 0 to z equals 4. That's how tall this thing is. And then v, which is the angle, it's the one that's going around all of these circles. We want it to go around the entire circle. So we just said v goes from 0 to 2 pi. And actually, I'm going to show a few more grid curves. Let's show 8 per variable instead of 4. So we've cut up our parameter domain a little bit more with more grid curves. And you can see on our surface, we have more of a grid going on. And you can see the circles that we found when we played Find the Circle. They are these horizontal circles. And again, if you want to open up this same GeoGebra app and put this in for x, y, and z, you can play around with the point and like check out how the different grid curves are drawn for different values of u and v. Okay, here is our third example. And surprise, we're going to find one more parameterization of this paraboloid. And it's actually very similar to the one that we just found. So going back to the one from before, we found a parameterization where our two parameters were essentially z and theta, because we want one parameter to pick out the circles and the other parameter to go around the circles. So for our third example, we're still going to make reference to these circular cross sections, except we're going to note that instead of every one of these having a different z coordinate, each of these circles, each of these circular cross sections has a different radius. So whereas before we were thinking about the circles as all having different heights, now we're going to think of them as all having different radii. And so that will lead us towards our roles for the parameters. We're going to say that one of our parameters is essentially the radii of all of these different circles. So we're picking out all of these different circles by looking at their radius. And then the second parameter is actually going to be the same as it was before, because once we've picked out all of these different circles on this surface, we're going to use this second parameter to traverse around them. So in other words, we're sort of thinking of the parameters as being like r and theta rather than z and theta from the previous example. And I think that this parameterization is the least obvious to come up with, which is why I'm showing it to you here. But it's sort of useful to know that it's a possibility, that you can let r, essentially the radius, be one of the parameters, and then the other one is usually theta. Now, to actually write down our parameterization, we just need to take what we wrote here, which is saying that we're looking at a bunch of different circles with different radii, and just parameterize those in x and y. So if u is our radius and v is our angle, x and y will be just u cosine v and u sine v. So in other words, these will parameterize a circle of radius u. Then to figure out what z is, we can just go back to our equation, and now that we know what x and y are, sort of like we did for the first example, we can just plug in x and y in terms of u and v and figure out what z is. So z will be x squared plus y squared, and so x is u cosine v, y is u sine v, and then we can simplify this a little bit by writing it as u squared cosine squared v plus u squared sine squared v. And maybe you can see that if we factor out the u squared here, we get, in parentheses, cosine squared v plus sine squared v. That's always equal to 1. So the z coordinate is actually just u squared. So our parameterization is u cosine v, u sine v, and then u squared. And before we go back to GeoGebra to look at how this actually looks, I just want to note that the fact that the z coordinate is just the radius squared is connected to the fact that in cylindrical coordinates, we would express this surface as just z equals r squared. So this parameterization sort of works out because we can let one of our parameters be r and the other one be theta. And then once we've done that, z is determined as just r squared. And so we just get the z coordinate being u squared. So back in our app, I've put the parameterization we just came up with, thinking of u and v as sort of like r and theta. And our parameterization domain is in the left here. You'll notice that I put u going from 0 to 2, whereas in the previous example, when z and theta were our parameters, I had u, which was like z. U was going from 0 to 4, so we got a paraboloid of height 4. Here, if u goes from 0 to 2, then z goes from 0 to 2 squared. So actually, the two parameterizations are tracing out the exact same paraboloid. It's just that we need to use different parameterization domains because the parameterizations themselves are different. And actually, let's do the same thing from before, where instead of looking at 4 grid curves in each direction, we look at 8, so that we can see the difference. Once I put in 8 here, we're cutting up the u and v directions into 8 equal pieces in our parameterization domain. And then we get this picture on the paraboloid here. And it looks like the same thing from before, essentially, with a very, very subtle difference. So if we look at it from the side, we can see that these horizontal lines, these are the horizontal circles, and they aren't evenly spaced. And that's because we have different roles for our parameters. So if you want to compare this to the previous one, hopefully in post-production, I figured out how to put the two pictures side by side. But in the left picture, we have the grid curves from when one of our parameters was z. And in the right, we have that same side perspective, except now it's a different parameterization, and one of our parameters is like r. And so these things are different, are spaced differently, different amounts apart. If we wanted to find a perspective so that they were spaced evenly apart, we could look at this from above. And we can see that these circles are evenly spaced. Whereas in the other example, if we look at it from above, we see that the circles are not evenly spaced because they are evenly spaced along the z-axis. And so what we're actually looking at for this picture on the left is the contour map for f of xy equals x squared plus y squared. Okay, so what I was trying to show you is that the difference between this parameterization and the previous one is subtle, but if we're clear on like how we're thinking about the parameters, we can really understand the reason behind why there are geometric differences in how these grid curves are set up. Okay, for our last example, we are going to find a I'm just kidding. We're going to find a parameterization of a sphere. So the radius of the sphere doesn't really matter. I just picked 3. And actually, there are a lot of ways that you could parameterize the sphere. You could play find the circles with this sphere and note that it has circular cross sections, just like the paraboloid, at different heights. But without playing find the circles, there's another way that we can write down a parameterization for this sphere, and that's using spherical coordinates. Because again, if we want to think about like what roles could our parameters possibly be, well, they could be like z and theta, but this is a sphere, and we know from thinking about spherical coordinates and the connection between that and like latitude and longitude, that a point on a sphere is determined by its latitude and longitude, or it's determined by phi and theta in spherical coordinates. So for this last example, we're going to set up a parameterization of this sphere where our parameters are acting like phi and theta. So again, I wrote b here in quotes because our parameters aren't going to be literally called phi and theta. Instead, they will reflect the phi and theta coordinates of points on this sphere. So to actually write down our parameterization, we're going to want to find what x, y, and z are in terms of our parameters, or in terms of phi and theta. And to get there, we need to start with the expressions for x, y, and z in terms of the spherical coordinates. So it's those hideous equations that are like x is rho cosine theta sine phi, y is rho sine theta sine phi. I have to look it up about half of the time because I don't remember it. So I think it's this. It's this. Yeah, we're good. It's this. So we start with this. This is x in terms of rho, phi, and theta, and y in terms of rho, phi, and theta, and z in terms of rho, phi, and theta. Now we want this in terms of just phi and theta. And the observation to make is that for rho, well, we're working on the sphere. This is x squared plus y squared plus z squared equals 9, which in spherical coordinates is just rho equals 3. Rho equals the radius of the sphere. So for points on the sphere, rho is fixed at 3. And so we can write down our parametrization by just saying, let's let u be phi, v will be theta, just because we've had v being theta the whole time. And then rho is just a number, it's just 3. So we really get x, y, and z in terms of 2 parameters. So we'll have x is 3 cos v sine u. Again, I'm using v for theta just to be consistent with our previous examples where v and theta were sort of the same. If you switched u and v here, it wouldn't really ruin anything, as long as you were consistent and made sure that you used the same parameter to model the same spherical variable. So 3 cosine v sine u, 3 sine v sine u, and 3 cosine u is a parameterization of a sphere of radius 3. And if you really wanted to, you could take these 3 things and plug them in for x, y, and z and see what you get. There's a lot of trig canceling stuff that you'd have to do, but you would eventually end up with, if you simplified this side of the equation after plugging this in, you would end up with 9, which means that the points given by this formula always satisfy this equation, so they always lie on this sphere. Okay, back in GeoGebra one last time, I've put in the parameterization we just came up with. It is definitely a sphere of radius 3. And you can see that the grid curves here are lines of latitude and longitude. And that sort of makes sense because phi and theta model lines of latitude and longitude on Earth. So the picture we would get when we fix phi or fix theta is just one of these lines. So the red curves here are fixed u curves. Remember, u was like phi. And the blue line here is a fixed v curve. Remember that v was like theta. I'll note just one last thing, that if we wanted not the whole sphere, but just like a part of it, like maybe we wanted just the part that lied in the first octant, the part where x and y and z are all positive. Well, to do that, nothing changes about our parameterization because we still want points on this sphere. We just want only some of the points. So to get the part of this sphere that lies in the first octant, we would restrict u. So u is like phi. We don't want points below the xy plane, so we want u to stop at pi over 2. And we want v to go only from 0 to pi over 2 as well, because that will guarantee that all of our points lie in the first quadrant of the xy plane. There we go. And so we get the portion of the sphere that lies in the first octant. So I'll recommend just one more time that while you're working with parameterizations, you try using this applet in GeoGebra. Again, the link is in the description for this video, and it's on the screen right now. You can use it when you're trying to come up with a parameterization to check if what you wrote down is correct. You can use it to explore what different parameterization domains do, and you can use it to play around with grid curves to see what they look like. I think it's really useful, and I hope you get something out of it. All right, that is parametrized surfaces. Or at least it's a start at some of the strategies that you can use when you're trying to come up with parameterizations of surfaces. As a quick summary, the things to look out for were essentially the things that I had on the right-hand side of the screen while we were working through this. You want to be on the lookout for surfaces that are graphs of functions, surfaces where you can find circular cross-sections, and spheres, because we have spherical coordinates and we can use that to our advantage. So I know there was a lot in this one, but I'm hoping that you'll be able to use this video and that GeoGebra app as a reference as you're practicing and as you're working with parameterizations for the rest of the semester. So thanks for playing along, and I will see you in the next lesson.